Welcome to Section 4 of Mathematical Proofs, and in Section 4 we are going to look at contrapositive proofs, proof by cases, and proof evaluations. So let's take a look at the first topic, and that is going to be contrapositive proofs. So, what is a contrapositive proof? Well, for an implication, P implies Q. For statements I put this in here. For statements P and Q, the contrapositive of P implies Q is not Q implies not P. And an important thing to note about contrapositives is, at least for implications, contrapositives are logically equivalent to the implication. And of course, we can look at a truth table to see this. And then we have not Q, not P, and then not Q implies not P. So we have our columns and our rows. So if we were to fill out this truth table, we have let's try to fix this one. We have true, true, false, false, true, false, true, false. We have true, false, true, true. And we have false, true, false, true, then false, false, true, true. And if we were to look at not Q implies not P, well, for this one it's going to be true, and then false, and then true and true. So if you notice, these have the same truth values for the statements P and Q. So therefore, we can use a contrapositive proof instead of a direct proof for the implication, and because it holds the same logical equivalence. And for some proofs, it is much easier or even preferred to prove or to use a contrapositive proof. So let's take a look at an example. So let's let x be an integer. So we need to prove that if 7x minus 5 is positive, then x is greater than or equal to 1. Okay, well, let's write out our proof for this. So let's suppose by way of contrapositive that x is strictly less than 1. So since x is an integer, there we go, since x is an integer, x must be less than or equal to 0. So 7x minus 5 must be less than or equal to 7 times 0 minus 5, which implies that 7x minus 5 is less than or equal to negative 5. So therefore, seven x minus 5 is negative as desired. So basically what we did in this proof is, instead of looking at the implication that 7x minus 5 is positive implies that x is greater than or equal to 1, we proved it by contrapositive. And remember, the contrapositive is not q implies not p. So we did not q, which is x is strictly less than 1. And then we proved that 7x minus 5 is negative by plugging in 0. Since it's an integer, it's got to be 0 if it's less than 1, or less than or equal to 0. So we plug that in and we showed that 7x minus 5 is less than or equal to negative 5, which implies that equation is negative for that range of x's. Okay, let's look at the next topic. We'll change colors here. That next topic is going to be proof by cases. So, sometimes in proofs, an element may possess one of two or more properties. So sometimes these properties may belong to a subset of the set being focused on. So such a proof can be divided into parts called cases. And a subnote here is cases can also have parts called subcases. So an example of this is a pretty known proof, is the triangle inequality. So the theorem is let x, let me do it like this. So let x and y be real numbers. So we need to prove that the absolute value of x plus y is less than or equal to the absolute value of x plus absolute value of y. Okay, so the proof is to let x and y be real numbers. We then proceed by cases on x and y. So the first case we look at is x is greater than 0 and y is greater than 0. So then we have x plus y is greater than 0. So we have the absolute value of x plus y equals x plus y equals absolute value of x plus absolute value of y. Now let's look at the second case. So we look at x is strictly less than 0 and y is strictly less than 0. So then we have x plus y is less than 0. So we get that the absolute value of x plus y equals negative x plus y equals negative x plus negative y, which equals absolute value of x plus absolute value of y. And then case 3, we are looking at x and y have opposite parities. So let's assume, without loss of generality, that x is greater than 0 and y is less than 0. We then consider two subcases, because we are looking at the parity of x and y, and x is greater than 0 and y is less than 0, so we have some different subcases that we need to look at for these values. So let's look at subcase 3.1, which is going to be x plus y is greater than or equal to 0. So then we have the absolute value of x plus absolute value of y equals x plus negative y, which equals x minus y, which is greater than x plus y, which equals x, the absolute value of x plus y. And now let's look at the next subcase, subcase 3.2. So for this subcase, we have x plus y is greater, or is less than 0, excuse me, strictly less than 0. So then we have the absolute value of x plus absolute value of y equals x plus negative y, which equals x minus y, which is strictly greater than negative x minus y, which equals negative x plus y, which equals the absolute value of x plus y. So these are all the cases that we need to look at for this theorem. So we have proved that the absolute value of x plus y equals, is less than or equal to the absolute value of x plus absolute value of y as desired. So by looking at the statement we were focusing on for the theorem and looking at all the possible cases of x and y and their respective subcases too, which was only for our third case, we were able to prove this inequality. The triangle inequality is what this is known as. So I'm just going to try to fix this square. And it still has a little bump on the edge of it. Yeah, that's better. All right. So here are some known theorems that were proved using cases. And I'm just going to copy and paste them on here so instead of having to write them, and we'll look at them. And these theorems are the four-color theorem. And this theorem stated that any map of contiguous regions can be colored in such a way that no two adjacent regions have the same color using just four colors. Well, this theorem was proved in 1977 with originally over 1,000 cases used. And another theorem, and I like saying the name of this one, this is the double bubble theorem. And this theorem stated that the most efficient way to contain two separate volumes is a double bubble. And this was proved in 1996 using 6 cases. And these are just some little depictions kind of what this theorem is. You have the two spheres, the two bubbles forming together, and you also have this shape right here, which is given a funny name, inner tube around a nuclear cooling tower. These were some theorems that my proofs professor brought up when we were going over proof by cases, so I just thought it was interesting. This is obviously one of the least efficient ways to prove a theorem, and this should be kind of a last resort proof, doing proof by cases, because it's so involved. Because if you remember when we were talking about math writing, it's normally better to come up with a quicker theorem because you have to think about your audience. But in some cases, that's funny, in some cases, you have to use cases for proving them because that's logically really the only way you can prove it. But yeah, just wanted to look at some real theorems that have been proved using this. 1,000 cases, that's probably was a very long proof to look over. All right. let's look at the last topic for this section. And this topic is going to be proof evaluations. So, proof evaluations are pretty straightforward. So, when given a proof, you need to check it for mistakes. So obviously this is just a really simple definition of what a proof evaluation is, and we'll look at a proof evaluation here in a few seconds, and you'll kind of see what mistakes you want to look for when evaluating a proof that someone wrote. So if a mistake is found, it's important to specify what the mistake is. And mistakes are just going to happen, and it's okay if you make a mistake, if someone else makes a mistake while writing a proof, and just math and learning in general, because mistakes are part of learning. They're part of learning math. So it's all right if you, me, or anyone makes some. You can learn a lot from them. So don't worry if you ever make mistakes while doing this, because you probably can learn the most from realizing where you went wrong and realizing what the right thing was to do. So back when I first learned how to write proofs, I had a lot of my fair share of mistakes, but that helped me learn what the right thing was to do. And here I am wanting to teach you about math proofs. So here's an example that we are going to look at for a proof evaluation. And that example is going to be this result, which is let x, y be integers. So then the square root of xy is an integer if and only if xy is a perfect square. And here's the proof that we are given of this result, and the proof says that let x and y be integers and let x equal 2 and y equal 8. And here's the proof we are given of this result, and the proof states that let x and y be integers and let x equal 2 and y equal 8. So then 2 times 8 equals 16, which is a perfect square. And then the square root of 16 equals plus or minus 4. So therefore, the square root of x and y is an integer as desired. So this proof on the surface might look kind of right, but let's write a proof evaluation here and try looking at some of the things that may be wrong with it. So the result is a biconditional. So a proof must involve analyzing both implications instead of focusing on only one. So in this case, we only showed that if xy is a perfect square, then the square root of xy is an integer. So additionally, a proof must include or must involve arbitrary integers and not specific integers such as 2 and 8 to allow for a more vacuum tight proof by generalizing it for all integers. And that is the proof evaluation for this proof that we were given. Basically, the mistakes that were found in this is that it was a biconditional. So the proof that we were given, it only proved one implication, because you remember a biconditional, it's only true when both implications are true. So since we only looked at one, this proof is not a valid proof. And also we used integers 2 and 8 instead of using arbitrary integers, so therefore we can't generalize it for all the integers that we are given to show that this biconditional is true. So those are some mistakes for this proof, and that's pretty much all you do for a proof evaluation. Alright, that is it for the notes for section 4, so I will see you in the examples for this section.